Good evening and welcome. My name is Maziar Nekovee. I'm the Dean of Sussex AI Institute and Head of Center for Advanced Communication, Mobile Technologies and IoT at University of Sussex. I am delighted to give this evening Sussex Universe lecture series on where are we with 5G and artificial intelligence and what may come next. So in this lecture, I'm going to cover a number of topics. I will start first by looking at 5G, the new generation of mobile communication technologies that is now available in UK and a lot of countries across the world, and where I have contributed quite significantly in terms of technology and standards. So I'll be looking at the timelines for 5G, some of the important use cases and capabilities of 5G that sets it apart from previous generation of mobile communication technologies. And then I will look ahead towards what may come after 5G, and that will be 6G, looking at what 6G capabilities might be and what sort of interesting and exciting application it can enable. And I will give you also an example of one of the technologies that we are developing at Sussex as an enabler for 5G. Then I will move to look at artificial intelligence, looking at what is general AI and AI, machine learning, and then I will focus a bit more on deep learning, and we'll give examples of some of our own research in applying deep learning to 5G and 6G technologies. And after that, I will discuss a little bit further expansions of artificial intelligence into engineering and industrial applications, and what are the new challenges that this will bring, and also what are new opportunities in terms of research and also skills. So starting with 5G, 5G is the new generation of mobile communication systems, and it follows the previous generations. So this is really a generation game starting from 1G. And what you see in this picture is Marty Cooper holding the first generation mobile device in his hand. And he's considered sort of father of mobile communications from Motorola Labs in US. So mobile communication, as we know, it started with first generation in 1980. The first generation of mobile communication systems was used to do voice and receive and send voice calls. And then this was followed by the second generation, which also enabled users to do other things such as SMS messaging. Now, the difference between 1G and 2G was 1G was an analog technology, while 2G was a digital technology. Then the big new breakthrough came with 3G. 3G was the first generation of mobile communication system that also enables data communication, so can be used for web and browsing, video transmissions, and so on. And that really opened a host of exciting new applications. But 3G was not as successful in terms of being a technology for mobile internet, and 4G was really the technology that basically led to breakthrough. And that was also at the same time where Apple iPhone was introduced. So 4G was a really technology focusing on data. And 5G is the next generation of mobile communication systems. And I will explain a little bit what new features and capabilities it brings. Now, one thing that we can see is that this new generation are introduced almost every 10 years. So every 10 years, there is a new generation of mobile communication systems. And also, as we go to higher generations, we are using higher and higher radio frequencies. With 5G, we are using extremely high frequencies. So what are 5G's industry timelines and what we may expect after this? Well, the technology itself is developed by industry, an industrial standardization body called 3GPP, Third Generation Partnership Project. And this consists of key industry vendors in telecom and mobile, which come together and agree on a set of technologies and standard that goes to every new generation of mobile communication systems. And this happens through releases. So subsequent releases are improved versions of the technology. So 5G really started around 2015, 2016, the development of technology, and it had a number of phases. The first phase was really focusing on making mobile internet faster and better. So 4G could achieve a maximum data rates of 1 gigabit per second, and 5G aimed to improve that by a factor of 20. So a really major improvement, which means that before you can read the label of a DVD, it is already transmitted over the air to you. But what is also important is that while previous generation of mobile communication systems were focusing on providing data, voice, and video, and so on, 5G is really has the ambition to become the critical network for a host of new industries and applications. So, and that's is what is now being still developed within the standardization. Well, looking at this, we also can sort of predict when we may expect 5G, may expect 6G. So we can expect that the work on research and development work on 6G would start around 2025, 2026, and we can expect the first commercial 6G technologies to be launched around 2029, 2030. Now, so what are the capabilities of 5G that sets it apart from previous generations? Well, these are usually in sort of breakdown in three different new capabilities. First of all, as I mentioned to you, 5G is much faster than 4G. So 20 gigabit per second, and this is basically the speed it may operate by 2030. So this is sort of a future speeds it can achieve. At the moment, for example, if you have a 4G handset, you may be able to achieve in UK around 40 megabit per second. With 5G, you could expect to achieve up to 1 gigabit per second. So that's already extremely fast for most of our applications now. And this is obviously not available everywhere, but as the coverage increases, we can expect to be able to achieve this sort of a gigabit per second speeds everywhere. So this is much faster, for example, than most of our home broadband. And this is really an important requirement to enable things such as augmented reality, virtual reality, ultra high definition videos, streaming and gaming on mobile handsets. And this is really focusing on the consumer market. Now, 5G is not only extremely fast, but it also reacts very, very fast. And this is quantified in terms of a latency. So the latency means that if you have a 5G mobile in your hand and you push a button to, for example, control a robotic arm somewhere, that robotic arm will react to you within a millisecond, obviously assuming that you're not at the end, at the other side of the world, because you cannot go faster than the speed of light. So this is really the reaction time to 5G signals. So it's 1 millisecond in 5G, and it was about 10 milliseconds in 4G. Now, these fast reactions are important for applications such as industrial robotic automation, for autonomous and connected cars, for health applications, and so on. So any application that requires very low latency, very fast reaction times can benefit from 5G's ultra low latency and also ultra reliable communications. We are also moving from an era that connectivity is not anymore human-centric, but we have cars, sensors, trains, devices, smart grids, utilities, all connected to the internet and to each other, factory cameras on factory floors. And this is basically what we call IoT, the Internet of Things, expecting to have 50 billion of such sort of connections potentially by 2030 or earlier. And 5G also enables this massive scale of connectivity to be available by then. Now, these sort of new capabilities of 5G, beyond being faster, really focusing on what we call the enterprise market. So areas such as health, automotive, smart grids, smart cities, smart manufacturing, and so on. Now, that's 5G, but what might 6G be? Well, first of all, typically, if a technology is introduced, it takes about 10 years or so to actually develop and standardize that. That means that research on 6G has already started, both in industry and academia. We are very much involved in 6G research at my center at Sussex. And these are examples from two leading telecommunication and mobile technology vendors, Samsung and Huawei. This is sort of their vision of 6G in terms of capabilities. So basically, what we expect that 6G is going to be much faster than 5G, is going to have much lower latencies, is going to be much more reliable. And one of the things that is probably going to be part of 5G is that we are going from gigabit per second mobile wireless connectivity to terabit per second. And this is obviously enormous further increase in speed. And why do we need that sort of speeds? Well, we need that sort of speeds to enable things such as holographic communication. It's very topical now with COVID, where we are all online and we use Zoom and Teams and so on. But wouldn't it be great if we can actually have a full holographic presence, for example, holographic presence for lectures, holographic presence in offices and so on. So bring us closer to the internet, although we are working remotely. Now, for that sort of applications, for full holographic, you would require terabit per second connectivity. so this is one applications that we may see with 6G, full holographic communication enabled by terabit per second speeds. So this is as I mentioned to you. So in this case, for holographic communication, if you look at the requirement, comparing with, for example, transmission of 4K or HK HD video, for that we may need between 35 megabit to 140 megabit per second connectivity. If you go with full VR, virtual reality, and AR, then we need up to 5 gigabit per second. So this can be supported by 5G, but for full holographic communication, we may need between 4 to 10 terabit per second speeds on our future devices. So that's why for that we would need 6G. Another example is digital twins or digital triplets, even people talking about. And this is really ability to be able to, in real time, replicate a physical system. In this case, is a car, but it could be a factory plant in silicon. And this can be used, for example, to predict maintenance issues in real time and address them, because we have a digital replica of the real system that we can fully analyze in real time. But we can also look at potentially having a digital human, so a digital replica of the human with in-body and on-body sensors. We can replicate human body and then basically transmit in real time the state of our body to this digital replica. Now that would also require terabit per second connectivity in order to send that sensor data from the physical system up to the cloud, where it can be replicated in digital. These are some potential applications of 6G. Now, as I mentioned to you, for 6G, we may need terabit per second mobile connectivity. Now, the challenge here is how we can go from what we have now to there. So the answer to this is something called the Shannon capacity formula. Claude Shannon, very renowned mathematician, but also telecommunication engineer at Bell Labs, who is also the inventor of the information theory that has wider applications in many areas. And he came up with this Shannon capacity formula, which says that the capacity of a channel, so that is really the speed of transmission, is proportional to bandwidth. So that's the amount of frequency that you have, and then logarithmically proportional to the signal that you receive compared to the noise in the environment. So obviously this means that if you bring your transmitter closer to your receiver, for example, in rural areas, we have that problem because the signal is not strong enough. So we need to bring our 5G mask closer to users in order to improve capacity. But the other way, maybe more smart and effective, is to increase bandwidth. So we have more frequency. We're able to, if we increase frequency, amount of frequency by 10, we have an increase of 10. While if we increase the signal by 10, we only have a logarithmic increase. So maybe 2 times or so, roughly. So that's why we can play with this. And in fact, in 5G, if we look at 4G, the frequency or bandwidth that is available was around 10 up to maybe 50 megahertz. Now 5G uses much higher frequencies in the sort of millimeter wave range, we call it. And that's because the size of the antennas are around millimeter. So you can imagine how small this 5G millimeter wave mask could be. You have maybe 500 megahertz or a gigahertz of new spectrum, and therefore you can increase capacity in principle by 10 times. So if we want to achieve terabit per second connectivity, we need more spectrum, radio spectrum. So where we go from to frequencies called the terahertz frequencies. These are frequencies that lie between what traditionally used for mobile or radio communication and light. And if we go to these frequencies, there are many new challenges. One of them is that the higher the frequency is, the more our signals attenuate. So and that is basically proportional to the square of the frequency. So if we simply go from, say, 100 megahertz to 1 gigahertz, we are increasing our frequency by a factor of 10, and that will result in 100 times attenuation of signals. Now, to combat that, what we need to do is to basically use antenna technologies that are able to focus our signal, and that can compensate for the fact of frequency increase. The higher the signals, the we need to have a more and more focused beams. Now, that is done in 5G already. So this is an example of Samsung's 5G system that was trialed in London. This has been used in order to offer gigabit per second connectivity wirelessly, so without using any fiber, from a base station to home users. Now, this system operates in this millimeter wave frequencies, so 28 gigahertz, and it has 1024 antenna elements. Obviously, because it's millimeter wave, these antenna elements are tiny. So this is the base station, so it's smaller than typical base station, but it has a very complex radio frequency and chip design in order to accommodate this 1024 antennas. If we go to terahertz frequencies, we may need, if we want to do the same thing and offer users terabit per second connectivity over the same distance, we may need to have 100,000 antenna element, and this is not scalable in terms of its electronics, there's energy consumption complexity. So at Sussex, we are developing alternative technologies to what is available for 5G, what we call crystal-based metasurfaces. So what is a metasurface? Metasurface is basically a surface where the electric properties are manipulated on a sub-wavelength scale. So, for example, for light, it will be on the nanoscale. For our applications, it will be on the microscales. So by manipulating these surfaces in an arbitrary wave, we are able to do very interesting thing with that. So typically, for example, if you have a ray of light and you that is reflected from a surface, that you will get a simple reflections. Now, by manipulating these surfaces, we can achieve that when a ray of light bounce on the surface, it will then reflect it back in a focused direction that we can then control with a electronic circuits. So that is the basis of how we can do create very focused beams in the terahertz range by using these metasurfaces, which are controlled here through an electronic circuit. Liquid crystals are crystals that their electronic properties can be controlled using voltages. So we can reconfigure this metasurface in an arbitrary way, the way we like, in order to create very sharp focused beam in terahertz. This is showing at this time is in still and development. So where we have a surface and you have these very sharp beams created in terahertz using a combination of liquid crystal reconfigurable technologies and machine learning in order to basically reconfigure the surfaces in order to achieve a desired beam patterns. So moving on to artificial intelligence. And here I would like to, obviously there is a lot of information about AI. So it's good to really explain a little bit what we mean by AI and what are different flavors of AI that are not being used. So we're talking about AI, artificial intelligence. The idea is obviously that we are able to replicate, say, the human intelligence in the digitally or in computers. And what is really catching a lot of attention is obviously the general artificial intelligence, or really the ability to be able to replace human reasoning and rationality, cognition, all of that with computer algorithms that can run on different platforms. That's general artificial intelligence. That is not achieved yet. We don't know when we or if we can achieve this sort of general artificial intelligence. The more narrower version of artificial intelligence is basically computer programs. So we're talking about artificial intelligence, I was talking about algorithms and computer programs. Computer programs that they can be cognitive, meaning that while usually when you write a computer code, you have something in mind, you write it for that purpose. Now that computer code have some parameters that can be changed, but the code itself doesn't change. Now with artificial intelligence, what we mean is that computer code can actually learn from the data that it receives and then reason and adapt, meaning that it can reconfigure its program, so to speak, in order to perform better. Now, that is artificial intelligence in a sort of bare bone definition. What is machine learning? Machine learnings are a set of algorithms, so a subset of larger artificial intelligence, that the behavior or their performance improves as they are exposed to more and more data. So we write these algorithms to do certain things, and we use them. That will gives us more data, and that data, when it feeds to our system, that help improve its performance. Finally, deep learning is a subset of machine learnings. And I will explain deep learning a bit more in details here, but basically deep learning uses neural networks, artificial neural networks, multi-layered, in order to basically perform this improvement by being exposed to more data. So here are various flavors of machine learning. We have supervised learning. Supervised learning is a learning where we tell our algorithms what, for example, we label our data, and then they can use that to improve their behavior. Unsupervised learning, we don't do that. Reinforced learning is also an approach where basically the system improves itself through real-time learning from data and so on. So just a little bit about deep learning. Deep learning came to prominence some years ago. So this is 2017, when the Google DeepMind's AI defeated the human Go champion. So Go is a very complex game, and the AlphaGo was able to defeat the world champion using a deep neural networks. So what is a deep neural network in a nutshell? But it sort of mimics the human neural nets. So it's an artificial neural network. It consists of an input layer with a number of nodes and an output layer. Now between these layers are a number of what is called the hidden layers. Now, each layer is connected. All nodes to each layer are connected fully to nodes in the next layer, and so on. But this connections has a certain weight. Now, depending of the weight, if the input layer receives an input, that will then trigger an input into the next layer or not. So if the weight is 0, for example, means that it will never be triggered. And basically the way the network works is that we start with a set of weights for all these layers, and then we feed into these network a set of labeled data. For example, could be images of dogs and cats. So we feed it into this. And then at the output, there is a outcome is that, for example, if the picture that is fed into is a cat, yes or no, in this case, or is a dog. Now, if we are feeding it a cat and it recognizes it's a cat, the neural network is rewarded, means, and that basically is a reward function. And that backtracks, and that is quite a sophisticated algorithm for that, such that the weights are accordingly readjusted. So by doing this with a huge amount of data, basically we configure the neural network into a system which are able to recognize cats from dogs. Now that's a very simplified, highly simplified explanation for how deep neural networks work. And in practice, how it is said that we start by training the neural net using a set of labeled data. So we have a number of pictures of cats and dogs, and we can label them for the neural network, feed it into that, and based on that, the neural networks weights configure themselves such that they get better and better in recognizing a cat from a dog. So that they create an internal model. This is not a mathematical model. It's not even an algorithmic model as such, but it's basically the ways that the weights are now reconfigured. And once that's done, then we validate the capability of the network by feeding more data into this. And this is in order to avoid overfitting, so that the network is really good, but because of that, it may have problems. So the network is really fitted with the what data that we have put into that, but any new data is not able to basically recognize it properly because of overfitting. And once that's done, once that validation done, the neural network now can be used to, for example, recognize cats and dogs. Obviously, for example, if we are looking at things such as face recognition, if our sample data has only, say, people captured in a certain countries, then the neural network can be biased towards only recognizing these faces, unable to do others. So we need to have a very diverse set of data sets in order to avoid that sort of overfitting. Also, unlike an sort of a algorithm that's written in a computer code or a mathematical formula, it is not very transparent actually what sort of model the neural network has formed. So obviously the applications go well beyond face recognition or recognition. So we can use it for classification. We could use it for diagnostic anomalies, for example, in things such as cancer diagnostic from X-ray images or other medical imaging, and recent breakthroughs have shown that the neural nets, when deep neural networks or other machine learning algorithms, when properly trained, they are always outperforms both human and the most conventional algorithms. So how does actually the neural network recognize as a cat or dog? Well, basically, if you have a picture of a cat or dog, it's pixelized. There's a number of pixels. Now, if this is not a picture of a cat and dog, it's a random, it's fully random, then if we go from one pixel to the other, there's no correlations between the pixels. But if there's a picture of a cat, obviously, there are correlations between the pixels. So the neural network is very good in finding these small scale or large scale correlations and then build a model based on these spatial and temporal correlations. So that's the basics of it. This is an example of some recent work that one of my students has done using deep neural networks for detection of radar signals. Now, why this is important? Obviously, one of the major applications in sort of a defense and battlefield situations. Radar signals, obviously, if they detect, say, hostile airplane, for example, that can be used, or many different applications. Now, and obviously, it's useful to be able to detect the presence of a radar signal in order to, for example, also to avoid that if you are exposed to hostile radar signals and you want to avoid that. But in order to do that, you have to first be able to detect that this is a radar signal that you're receiving. And these can be changed now using deep neural network. And these are different signals or radar signal technologies. We call it modulations that can be used. And basically using deep neural networks, we are able to train a network, and this is implemented in hardware in order to recognize radar signals among the multiple of possible signals. So this is a classification problem that deep neural networks can do very well. The other examples is what we are doing on using deep neural networks in designing 6G modems. Modem is basically a chipset, and this is a Qualcomm chipset, for example, that is in your mobile device, which does all the transmission and reception of 4G, 5G, Wi-Fi, and other signals. Now, the traditional modems are designed, they consist of a number of signal processing blocks, extremely complex. Signal processing to basically digitalize voice, video, data, and then transmit them over the air using one of these technologies. Now, these are designed through industry standards, and then they implemented, and they cannot be changed, they cannot be improved, they can be only improved manually. So what we looked at, and this is the work we did with Samsung, collaboration with Samsung, is how about replacing this whole signal processing blocks with a deep neural network, which is something called autoencoder. So what is the benefit of that? Well, if we can do that, and it is possible to do this, then basically we could feed in data into this modem as it's being used, and that can then improve the performance. So it can change to different applications and environments, your handset, as your mobile, as you're moving around. It collects data and it gets better and better. And also the development cycle of communication systems is 10 years. This is quite long, but having this sort of a deep neural network systems, we are able to also reduce the development cycle. So that is likely to be a component of 6G. So with 6G mobile in your hands, it will be powered by artificial intelligence. Now, a very interesting experiment that we did is that we looked at a number of these deep neural networks that, and they basically are transmitting and receiving, and they cause interference to each other. You want to see what happens in this case. Now, when there is interference, the neural network will react in order to improve performance and change some of its internal parameters or internal model, and that will then reduce the interference. But other neural networks or other deep neural networks will react to that. So this is, for example, what we get. This is two of these transmitter-receiver pairs neural networks. They are transmitting and receiving, and they are causing interference to each other. And by reacting to that interference, they will change their internal they will change their internal deep neural network in real time, and this is visualized here. So this what we also can so that's some examples of different applications on neural networks in telecom sector. So obviously, still the large body of applications are, I would say, in software systems. The next frontier of AI will be AI going into engineering systems, into what we call industrial AI. Also, and a really good example of that is autonomous cars, where they use computer vision and other machine learning algorithms very intensely. Now, other examples are in future smart manufacturing, different type of robotics. Here is, for example, of consumer robots, and I mentioned the mobile communication, 5G, 6G. Now, when machine learning and AI are applied to such critical engineering systems, obviously there will be new challenges in terms of their reliability, mission critical usage, and so on. So just to give an example, for example, this is a case of Tesla Model 3 that was crashed in 2020 when it was in the autopilot mode, crashed into a truck, and it was not possible to understand what exactly had happened, but it was a sort of a AI singularity, possibly. So obviously being able to predict and definitely avoid this sort of risk is extremely important, also from perspective of legal and liability requirements. So predictable AI is very important. We don't have that as well. We know that AI gets better with more data, but there are also cases that it can perform in a very unpredictable way. Sustainability is something that is extremely important, because as AI becomes embedded and in every object and different sort of systems, one challenge, especially with deep neural network, is that they are very data, but also CPU time hungry. So they consume actually quite a bit of CPU time and data, and that also means consuming quite a bit of energy. So sustainable AI an energy efficient AI is still a challenge. Also, when AI algorithms are used in order, for example, to use in things such as maybe job applications or other um, applications, legal and so on, it is a need to be able to explain what actually has led AI, what was the reasoning behind AI algorithms to reach a certain conclusion. Reliability is very important in also in engineering. So we know that all systems can fail, but using probabilistic methods, we are able to make estimates of the probability of failures and therefore mitigate. Now, we don't have that sort of things at the moment with AI algorithms. Also, AI is going to be used more and more in all kind of systems. So if all these systems relies on cloud computing for their AI, that will cost a lot of energy. It will be needs latencies and so on. So things such as edge AI and network AI are helpful in there. And finally, as I mentioned to you, machine learning in particular and deep learning is extremely computing time, CPU intensive. So far, AI has been implemented in digital computing systems, but there are new paradigms for computing, such as neuromorphic computing, which is an analog version of computing, much closer to how our brain potentially functions. It's not digital. And optical computing. So at the moment, we are using electronic computers, using electrons for as a main carrier of information, but optical computing could be a breakthrough, photonic, because it's more energy efficient and it can also be much less complex. And finally, quantum computing, obviously, that's something that will coming in the next decade or so, and the combination of AI and quantum computing will result in quantum AI with fascinating opportunities there. So there are a lot of new challenges, but that's in a way makes it also so interesting. So AI, this is from a very recent report from Stanford University, Artificial Intelligence Index Report 2021. The graph here on the left shows the number of peer-reviewed publications in AI starting from around 2000, and we see a steep increase in the number of publications. So there's lots and lots of research happening on AI, obviously, and this also translates in patents. So industry and large and small startups, both startups and large companies, are really turning this into patents and technologies. So that's very that is excellent, but there is still a huge room for research in a number of areas. Now, what is also interesting from a university perspective is the skill sets for AI. Recently, I read an article in Mobile Europe, which is basically a magazine that is for telecom professionals and R&D leaders. Now, in the telecom industry, AI is as one of the top technologies for future and near future. But the biggest obstacle that the CEOs in a telecom CEOs pointed out to was the lack of skills. And so this graph is very interesting because it's showing the relative, so relative to population, AI skill penetration by country. And interestingly, India comes on top, followed by United States and China. In this case, at least based on this. And then there are other countries. UK is quite high up, but there is a need, obviously, for in all these countries for much more skilled AI graduates and workers. So there are great opportunities in AI, huge opportunities. And in particular, as AI moves from software towards engineering systems and towards what we call cyber physical system, there will be more and more opportunities in industrial artificial intelligence and engineering artificial intelligence as well. So with that, I would like to thank you for listening, and we're delighted to take questions either in real time, or you could always email me. Thank you very much.
Well, we hope you enjoyed this video. Once again, I've got to ask, if you did enjoy it, please give the video a like and subscribe to our channel to see our future updates. If you're interested in the future talks we've got coming up, do visit our website at bit.ly/SussexUniverse. And remember, if you're watching live, the live Q&A starts now at the Zoom link in the description down below.